in this audience. She will speak on Gradient Ricci Solitons conformal to pseudo-Euclidean space.
Okay, thank you very much. I would like to thank the organizer for inviting me to give this talk. And I will be talking on this Gradient Ricci Solitons conformal to pseudo-Euclidean space. So yesterday in Kao's lecture, we had a very nice overview of the Ricci Soliton theory for Riemannian manifolds. So here I will start telling you about the Ricci Solitons in the pseudo-Riemannian case, and the basic definitions are the same. You just consider a semi-Riemannian manifold, n-dimensional with geometric G, and if there exists a smooth vector field X such that the Ricci of metric plus the lead derivative of G with respect to this vector field is equal to rho times G, rho is being a constant, then you say that you have a Ricci soliton. If there exists a differentiable function f that we call potential function, such that the gradient of f is the vector field x, then we say that m and g is called the gradient Ricci soliton, and f is the potential. So in this case, this equation reduces to this one, where you have the Hessian of f. And we say that the Ricci soliton is shrinking if rho is positive, steady if rho is equal to 0, and expanding if rho is less than 0. So when M is Riemannian, so one requires a manifold to be complete. In the case of semi-Riemannian, usually one does not require the completeness because it's more delicate in this case. And so this is what we are going to do. We are not considering completeness. Now, the Ricci soliton equation was initially introduced in the Riemannian context by using the Ricci flow Ricci flow was introduced in '82, and then the Ricci solitons came up as special solutions of the Ricci flow. Now, Friedan in '85 considered the physical aspects of the Ricci flow, and this is when the pseudo-Riemannian case came in. Now, there are essential differences between Riemannian case and the pseudo-Riemannian case. Okay, as you know, the Ricci solitons are important because they are extensions of the Einstein manifolds. This is when f is a constant. They correspond to self-similar solutions of the Ricci flow. And also they are important in understanding the singularities of the Ricci flow, and they are critical points of certain functionals. Examples and some known results, and I'll be very brief on that. So when you consider the Euclidean case, you consider f being a constant times x squared over 2 plus the g times x of b, b being a vector and c a real number. These are the potential functions for the canonical Euclidean case. So, and the being shrinking, steady, or expanding will depend on the sign of A. Now, Bryant proved that there exists a complete steady gradient Ricci soliton, spherically symmetric for any n, and this is called the Bryant's Ricci soliton. Now, Kao Chen, so as I said, I'm not doing an overview, I'm just mentioning some of the aspects that I will need later. So Kao Chen in this paper of 2012, they showed that any complete steady gradient Ricci soliton locally conformally flat up to omega t is either isometric to Bryant's Ricci soliton or it is flat. Now, Lorentzian Ricci solitons have been studied recently by many people like Brozos, Vasquez, Calvaruso, Batat, Garcia, Rio, Onda, Galcavino, Fernandez, Kim, Lee, Choi, etc. This is an example of how things change from the Riemannian case to the pseudo-Riemannian case. For example, three-dimensional Lie groups do not admit left-invariant Riemannian Ricci solitons. However, the Lorentzian case allows the existence of expanding, steady, and shrinking left-invariant Ricci solitons. This was proved recently by Brozos, Vasquez, Calvaruso, Garcia, etc. Another recent result also, if in the pseudo-Riemannian case, they gave a local characterization of the Lorentzian gradient Ricci solitons, which are locally conformally flat. This is in terms of the gradient of the potential, being zero or non-zero in open sets. Okay, so but what I'm going to tell you, this is the joint work with Barbosa and Pina, and we consider gradient Ricci solitons conformal to pseudo-Euclidean space, which we also require to be invariant under the action of an n-1 dimensional translation group. So we consider Rn with the canonical metric. So we are considering coordinates x1, xn. Gij will be delta ij epsilon I. These epsilons I are plus or minus 1, and we require at least one of them to be plus 1. So what we do is we consider a basic invariant of the n-1 dimensional translation group, and this is given by xi being alpha I, xi, alpha I being real numbers. So what we want to do is find phi and f depending on this basic invariant, and we want g bar to be conformal to g by this conformal factor is phi square, and we want the g bar to satisfy the Ricci gradient equation, Soliton equation. So what we are going to do is obtain first necessary and sufficient conditions for the existence of g bar, necessary sufficient conditions on f and phi. And what we will see is that these conditions depend on the direction alpha. Alpha will be the vector that we can consider taking alpha I ddxi. Now, depending on this vector alpha being a null vector or space-like or time-like, the conditions are very different. And if alpha is a null vector, then the gradient Ricci soliton will be necessarily steady, but not in the other case. Okay? However, what we are going to do here is that we will solve the problem completely for the steady gradient Ricci solitons conformal to G, which are invariant under the n-1 dimensional translation group. As we will see, the non-steady cases, they should be studied a little bit more. I mean, it's that we couldn't deal with it. Okay, so what we will see is that if the direction alpha is time-like or space-like, then the functions f and phi depend on the dimension n and a finite number of parameters. If alpha is a null vector, then we have an infinite number of solutions. We have infinitely many solutions. In this case, given a phi, we have to solve an ODE, one can explicitly solve it, to find the potential function f. And in this case also, as we will see, the scalar curvature will be 0. Now, if we restrict these metrics in the Riemannian case, meaning all the epsilons I will be 1, then the metrics G bar are not complete. Okay, so let's start with the program here of getting the necessary and sufficient conditions. So we are taking R and G coordinates. Gij will be delta ij epsilon I, and we consider f and phi to be the conformal factor. So we will get R and G bar to be a gradient Ricci soliton if and only if f and f as a potential function, if you have this system of equations that f and phi and f have to satisfy. So this is nonlinear second order, but this is just requiring to be conformal. So we want to solve this system here whenever f and phi depend on xi, where xi is this basic invariant of the translation group. So whenever this alpha is not a null vector, then without loss of generality, we can consider to be this sum of this norm to be plus or minus 1. Okay, so first, in this theorem, we have the necessary and sufficient conditions that have to be satisfied for these solutions depending on Xi. So we have two. So we have two cases here. Either we have a space-like or time-like vector or a null vector. So G bar will be this gradient soliton with f as a potential function. If f and phi satisfy this system here, whenever alpha is space-like or time-like. And just one equation in the case where alpha is a null vector. Here, observe that we have the rho, which is this constant here. And as I said, this is nonlinear, second order. And we can deal with a system whenever rho is equal to 0. The rho different from 0, so the shrinking or the expanding case have to be studied, still studied. Now, in the case of the null vector, then necessarily you have rho to be 0. And the equation is just this one. So what we have to do is solve this equation, this system in the first case and the equation in the null case. Now, I'll give you two results which give you f and phi being the gradient solitons, Ricci solitons, in terms of Xi. So consider this phi being plus or minus, according to this sign here, being a constant times this is a polynomial in xi, and this is an exponential, the exponent which depends on the dimension, and f is given in terms of logarithm of this expression here. So this is the case where we have space-like or time-like. So if we consider g bar to be g over 5 phi to the square, then these will be steady gradient Ricci solitons, and f plus or minus will be the corresponding potential functions. So these are defined on a half space, determined by the dimension and this constant. And as I said before, in the Riemannian case, g bar is not complete. Another one is the following. This is more elaborate. The other one is explicit. This one has two steps to get to the solutions. So we have this Xi, assuming that it's space-like or time-like, and we define V of Xi and H of Xi as follows. V has to determine this ODE. You see, it's a first order ODE. Here you have V, and these exponents depend on the dimension, and these constants A, B, C, and D depend only on the dimension of the space. So you get V solving this ODE, and H given algebraically in terms of V. Then you get phi and f by integrating the simple equations here, and then G bar, given as g over phi squared, will be a steady gradient Ricci soliton with f as potential function. So we will see later a proof of these results. But so we have two different results for the case where alpha is space-like or time-like, and this result tells you that these are all solutions. So it's telling you that if you want phi and f to be invariant under the n-1 dimensional translation group, with Xi as a basic invariant with alpha being time-like or space-like, then phi and f are given as in theorems A and B, as I said before. So this solves completely the problem for the steady case. Now the result, the steady case and alpha being space-like or time-like. In the case of the null vector, then what we see is the following. You can choose the phi of Xi, any non-vanishing differentiable function, and you have Xi being a null vector. Then we define f of xi being n minus 2 is integral involving the phi. Then f will satisfy this equation that we had before, which in the case of null vector, we just have one equation involving phi and f. And then we have the steady gradient Ricci Solitons with f as potential function. In this case, the scalar curvature of G bar is flat. Okay, so let's just see a couple of examples using theorem C, the last one, which gives you an infinite number of solutions. So here, for example, we choose phi to be a constant times e to the ac, a non-zero. In this case, and we are assuming that alpha is a, so the constants alpha I satisfy this being the same thing as alpha being a null vector. Then using theorem C, we get f of xi given explicitly in terms of xi and exponential. So this will be a steady gradient Ricci soliton, and f will be the potential function. This is another simple example. By choosing phi to be xi squared plus 1, and you solve the ODE that you have to solve to get the f, and you get f explicitly given involving logs, a rational function here, arctangent, etc. So these are steady gradient Ricci solitons that come up by applying theorem C. Okay, so now let's see a little bit of the proof. So the first result that gives you how to get the phi and f in the case of conformal metrics. So you get G bar is 1 over phi squared G. Then you know how to get the Ricci of G bar in terms of the Hessian of phi in the metric G and Laplacian and gradient. And then you plug into this equation here of the Ricci solitons, the gradient Ricci soliton, and you get that this equation is equivalent to this system of equations in terms of phi and f. And you still have rho here, okay? So you find out what's the Hessian of f in terms of G bar, and the substitute into this equation here, and you get exactly this system of equations here. This is for the mixed derivatives of phi, and this is the double derivative of phi. So what you have to do in the case of conformal, just solve this system of equations, overdetermined system of equations. Now, if you restrict to the case we are working on, which means that you want f and phi to depend on xi, then you substitute the derivatives of phi and f in the first equation, and you end up getting this one here. Observe that you have alpha I, alpha j here and here for I different from j. Now, if there exists I different from j such that alpha I, alpha j is different from 0, then this equation reduces to this one. And the second equation you plug in and you get this expression here. This is the norm of alpha in the metric G. Okay? And here you have the rho. Now, if alpha is space-like or time-like, then as we know, the norm of alpha will be plus or minus 1. You plug into that, and you get that the system of equations reduce to this pair of equations here for phi and f. And if alpha is a null vector, then because of this norm being 0, sometimes it doesn't work. Because this norm is 0, then rho will be 0, as we saw here. This being 0 then implies rho to be 0. And then the equation, and we get just the first equation, which is, which is this one here. Okay, this one. Now, if for all I different from j, alpha j is equal to 0, then this means that xi just is one variable, one of the variables, xi naught. So the first equation is trivially satisfied for all I different from j. And the second equation for I equal to I naught or I different from I naught reduced to the same system as we had before. But this is just, the C depends on one variable. Okay, so now, as I said, the system that we have to solve is this one here, for the case in which we have alpha being a space-like or time-like. So now we see the proof of theorem A and B in the case where alpha is space-like or time-like and considering rho equal to 0, so the steady case. So in this case, F and phi have to satisfy this system of equations here, this one here, rho being 0 and alpha being space-like or time-like. And we introduce a notation we called H to be F prime and phi prime over phi to be G. This will reduce the system from second order to first order system. And so the system reduced to this one here. Now from these equations it follows that we have this relation here involving dH and dJ. And in order to study this system, we just take G to be H times V. So the two cases that we have in theorem A and B are obtained by considering V to be a non-zero constant or a non-constant function respectively. So the proof of theorem A, if you take V to be a number n, then we substitute G as n times H in the system and you get H prime to be equal to this expression from the first equation and this one from the second equation. So comparing the H primes, you get what the constant n has to be. So n is given by this relation here, algebraic relation. So n has to be a constant. You have two solutions, which depends just on the dimension of the space. And H prime over H squared, you go back here, and it gives you, again, the H in terms of the dimension. So integrating, you have H prime, H given plus or minus because of two signs, and G plus and minus given in terms of the dimension and this constant B. So since H is F prime and phi prime over phi is J, then we get explicitly given in the case where this V is a constant, non-zero constant. So this is the theorem A. And okay. So what it tells you is that G bar, when alpha is space-like or time-like, is determined by the dimension of the dimension n and a couple of constants. And it is defined in a half space. And moreover, in the Riemannian case, G bar is not complete. How do we get this result? Is that in the case of in the Riemannian case, all the epsilon I are equal to 1, so the norm of alpha is equal to 1, and you can explicitly compute the sectional curvature in terms of the dimension n and the constants. Moreover, here, the alpha i's come up. Yeah? So you find out that G bar is not flat, and it's not isometric to Gradient Ricci Solitons, so it follows from Carl-Chan theorem that G bar is not complete. Now, in the case of theorem B, we are taking V to be a non-constant function. So we substitute G as HV in the system. Without loss of generality, we're assuming that H is non-zero. So we get dH over H written in terms of dV with this notation that we introduced before, A, B, C, and D in terms of the dimension. This equation here reduces to this one here. And so from this equation, we can integrate and we get H in terms of V and the constant which involves the dimension. So we recall that we want to solve the system of equations. So since G is equal to HV, the first equation reduces to this one here. And using the fact that V prime is different from 0, from both expressions of H prime, we get this one here. Now we plug in h, we plug in this expression here, and we get just an ODE for v, which depends on the dimension. Yeah? Now, so let's go back here. Once you solve this, you have v. You go back here, you have h, because it's determined in terms of v. And then you go to g, and you have h times v will give you the g. Now go back and, oops, okay. Now integrate for phi and f, and you get the result for the case, the proof of theorem B. So when v is not constant, the steady gradient Ricci Solitons, which when alpha is space-like or time-like, is determined by this function v, which satisfies an ODE in terms, given in terms of the constants of integration and the dimension. Again, in the Riemannian case, G bar is not complete. One computes the the sectional curvature, and you get it explicitly, and you find that the metric is not flat, it's not isometric to Bryant Ricci Soliton, then it's not complete by Cauchy's theorem again. So the theorem that tells you that these are all the solutions in the case of which are invariant by the n-1 dimensional translation group, whenever you have a space-like or time-like vector, then f and phi and f are given just those in theorems that appeared in theorems A or B. So the proof is now very simple, because once you have rho equal to 0, you introduce h and g in terms of f and f prime and phi prime, and we want to solve the system of equations here. Now the solution of this system is always given in terms of h times v. So by considering v a non-zero function, theorem A and B give the solution of the system whenever v is constant and whenever is a non-constant function. So this shows you that the problem is completely solved in this case. In the case of the null vector, then we consider phi in terms of xi. Now here we have a null vector here, and as we saw before, the conformal metric G bar will be a gradient Ricci Soliton with f as a potential if and only if rho is equal to 0 and f has to satisfy this equation, which is determined by phi. This is actually a first order in f, because you can reduce it for the f. So once you have phi chosen, then you can find out what the f is, how to determine f. So f prime will be this integral in terms of phi, and f will be given in terms of phi and derivatives, etc. So in this case, G bar has scalar curvature 0. So how do we prove this? Is we consider K bar will be epsilon I phi square Ricci of G bar I. This is the sum. And so we find out that the K bar is given in terms of epsilon I. That's the sum of epsilon I phi square, and this is a Hessian of f. Now the Hessian is given in terms of alpha I square, and this term, which is the same for any I. So you plug in here, and you end up having epsilon I alpha I square, and this term here, and then this shows you that K bar is equal to 0. So this is constant scalar curvature. And I guess this is it. Thank you very much.